Hi, in this video I am going to demonstrate how I use the microcontroller and some basic control theory concepts to improve the step response of a series RC circuit. For that, I use a DSP33 EV microcontroller, but keep in mind that any other chip that has PWM, ADC, and UART capabilities should work. The PWM output pin is used for applying the input voltage on the whole RC circuit, while the ADC input pin is used for measuring the voltage across the capacitor. Finally, both of TX and RX pins are used to send and receive data with the computer through the serial port. The communication on the PC side is managed with this user interface, which enables me to specify the parameters of the experiment, namely the input voltage in case of an open-loop control, or the set point and the PID constants in case of a closed-loop control. The time response is plotted in real time based on the data received from the microcontroller. The loop that runs on this latter consists of 3 steps. To begin with, the ADC module measures the voltage across the capacitor. Then, the PWM module generates a suitable command signal, according to the parameters specified previously. Finally, the UART module sends the measurement for plotting. This loop is repeated each 10 milliseconds, which is sufficiently faster than the theoretical time constant. Let us now talk about the experiment in itself. I started by examining the open-loop behavior of the system. By applying a 1-volt step input, I observed that it reaches 63% of its final value in 100 samples, resulting in a time constant of 1 second. The plot also showed that the final value is reached within 2% in 4 seconds. Now that I had a good model of the system, I intended to improve its transient response while having its steady-state error driven to 0 by using a PI compensator. The closed-loop transfer function of the system is essentially a second order with an additional 0, which I'm going to ignore for the sake of simplicity. In this experiment, I wanted a twofold reduction in settling time and an overshoot that does not exceed 20%. For that, I'm going to use these two equations, which link the desired requirements to the damping ratio and net wear frequency. By matching both denominators, I found the value of both constant, which satisfy the specifications set before. But applying these values on the real system showed a response that does not meet the desired specs, and that is due to the presence of a 0 in the numerator. This meant that further tuning was needed. For that, I used this online simulator. After a few iterations, I found out that by lowering the integral constant by a bit, the specs are met again. The real system can now reach the set point in 2 seconds, and does not overshoot more than 20%. I hope that you enjoyed this demonstration, and I thank you for your attention.